Okay, we are going to discuss inverse trigonometric functions and their derivatives and logs and their derivatives in this presentation. So you can see from the figure that the sine function y equals sine of x is not one-to-one using a horizontal line test. So what that means is the vertical line test discusses whether a function is a function, whether a graph is a function if it passes the vertical line test. But the horizontal line test is the complement to a vertical line test. It's talking about for every output, does it have a single input? And in this case, we can see that that's not the case. We have an output of +1 in many different places of this curve. Now, the idea of a function being one-to-one is a bit advanced of a concept, but if you pursue a heavy math career, you will eventually take abstract algebra where you really dive into set theory and what it means to be one-to-one function. Okay, when we take a look at this sine function and we make it one-to-one, then we have to restrict the domain. So notice that if we restrict the domain, and this isn't the only restriction that works, but it's one of, if we restrict it from -π/2 to π/2, we see that it is not only passing the vertical line test, but it also passes the horizontal line test, making this function now one-to-one. The inverse function of this restricted sine, f, exists and is denoted by sine raised to the -1 or arcsine. They mean the exact same thing. And sine raised to the -1, you don't actually raise the function to the -1 power. It's a notation for inverse function. But essentially, raising it to the -1 power does compute the inverse function. Now, you guys learned about inverse functions back in pre-calculus, possibly even college algebra, depending on when the topic arose. And recall that in order to find an inverse, you switch the x and y's and resolve for y. If we're talking about algebra functions, and I was talking about a linear function, for example, then let's say we're looking at y. Hold on, let's get my notation tool out. Y equals 2x minus 4. If I wanted to find the inverse to this line, I would first start by switching the x and y's, and then resolve for y since we're very much used to seeing y equals formulas. I would add the 4 to the other side, and then divide by 2, giving me y equals 1/2 x plus 2 is the inverse line to my original line. Okay, so switch the x and y's and resolve for y. Now, in the case of sine function, when we switch the x and y's, the way to get a variable out of the sine function, remember, you cannot divide by the word sin. That is not a thing. You have to take the inverse of the sine function in order to release the y variable. So the cancellation of equations for inverses becomes the inverse sine of sine is equal to x, and the sine of the inverse sine is equal to x. Same exact concept as we did in algebra class when we were trying to release an x from, let's say, the square root function. Hopefully you guys all recall that in order to do that, we square both sides. Okay, so we square both sides because x squared is the inverse function to the square root function. So we would get y squared is equal to x. Okay, so that would be our inverse function if we were to look at inverses between algebraic functions. Let's actually find the inverse. So let me prove that to you. So if we look at y equals x squared and we went to switch the x and y, so x equals y squared, We would then take the square root of both sides, technically needing the plus or minus that square root principle. So y would equal plus or minus the square root of x. Now, it's an or statement because if you drew both on the coordinate plane, we would see that it is no longer a function. It doesn't pass the vertical line test. Same would be true about the sine function. If we did not restrict the domain and make it 1-to-1 first, we would not be able to take an inverse and receive a function in return. Okay, because the function would not pass the vertical line test when we flipped its horizontal axis into a vertical one. Now, when it comes to, oh, and here's the graphs that I was talking about. Once we restrict, notice that it just mirrors, but if we did not restrict the domain, then it would continue to be that repetition curve and therefore not passing the vertical line test, and it wouldn't be a function. Here is the derivatives of all the inverse functions to our 6 basic trig. And essentially, this is just going to be another one of those charts that you keep in front of you when you are working with inverse trig. It's a memorizing thing because there is no easy way to derive these formulas, and they're quite time-consuming to derive. Let's try some examples. So let's calculate the derivative of inverse sine of a polynomial 3x to the 4th plus 8x plus 2. Now, first, let's recall that the derivative of inverse sine from the last slide is 1 over the square root of 1 minus x squared, where x is the inside function. So recall we have something other than x inside this function, which means we are going to have to perform a chain rule. Okay, so we're combining rules now. So our first order of business when working with the chain rule is to focus on the outside function. So the derivative is going to be 1 over the square root of 1 minus the inside function squared, which is that whole polynomial, 3x to the 4th plus 8x plus 2, times the derivative of what's inside by the chain rule. So we have 4 times 3, which gives us 12. Come back up and subtract 1 on the exponent. If we look at 8x, the derivative is just the coefficient 8, and the derivative of the constant 2 is 0. Now, the only other thing I can do to simplify this is to take this and put it in the numerator so that it's one compacted fraction, but it doesn't matter for simplification purposes. You can just leave it as seen. Let's try another one. So this one is y equals tan inverse of 2e to the x. So again, because the inside function is more than just x, we have ourselves a chain rule. Let's recall the basic inverse derivative of tangent. So when we're taking the derivative of the tangent function, it is 1 over 1 plus x squared. So when taking the derivative of the overall y function, we do the derivative of the outside first. So we have 1 over 1 plus the inside function squared, which is 2e to the x. And then we multiply by the derivative of what's inside, which is 2e to the x. Okay, so the more organized you are, and again, you need to always focus on the bigger picture. What is the outside? What is the inside when referencing the chain rule? Now let's explore the derivatives of the logarithmic functions. So we have the derivative of a log base whatever, because this log, if there is no a, it's defaulted to 10. If it's not a base 10, it has to be written. So be comforted that if you don't see a base written, it's just 10. And the derivative is 1 over whatever is inside the log x times the natural log of the base. For our natural log, the derivative is very simple. It is 1 over x. And that's because the base of the natural log never changes. It's always e, the number e, okay? And 1 over x times ln e, ln of e, they are inverse functions, which we just learned about. And inverse functions cancel each other out, giving us a 1 in that case. And that's why it's just 1 over x. Let's try some examples. So let's differentiate the function ln of x cubed plus 1. So recall that the derivative of the basic ln function that we just saw was just 1 over x, where x represents the inside function. We look over here, we see that there is more than just x inside this log, meaning that we need to perform a chain rule. So the outside function, which is the natural log, we will handle first. The derivative of the natural log is 1 over whatever is inside. And then the chain rule says to then multiply by the derivative of what's inside, which is 3x squared plus 0, because the derivative of a constant is just 0. Take a look at the next example. So our next example is the y is equal to the natural log of sine of x. Okay, well, again, inside that natural log, I see that there is something other than plain old x, and that is what constitutes us using a chain rule. So now I identify the natural log as our outside function, so we start there when taking the derivative. The derivative of the natural log is 1 over the inside function, untouched. Remember, never change two things at once. Never take the derivative of two functions at the same time. The chain rule then says multiply by the derivative of what's inside, which is cosine of x. So this is cosine over sine. Now, sine over cosine is the tangent function. So cosine over sine actually is the cotangent function. So if we wanted to reduce this or simplify, that would bring us back to knowing our relationships between sine and cosine in every one of the trig functions. Next example, y is equal to log base 5 of x. So recall that log base a of x, when taking the derivative of this common log is what it's called, we are 1 over the inside function times the natural log of the base, which is just a number. So our derivative of y would be 1 over x times ln of 5, which ln of 5 is just a number. I don't suggest that you put it in your calculator and find out what that number is, because it's going to be a decimal. It's not going to be exact, and we don't want to change an exact derivative to an approximate one. The next example is log base 10, which again, I didn't actually need to emphasize the base 10. This could actually be written without a number here, and I'd still know it was base 10. But for the purposes of just learning, I put it in there. Now, I'm going to take the derivative, and I notice that this has something other than x inside. So that constitutes a chain rule, where I recognize that the common log is the outside function, so I'm going to handle the outside function first. 1 over the inside function, 2 plus sine of x times the natural log of the base, ln of 10. Now that's just the derivative of the outside function dealing with the common log. Then we need to multiply by the derivative of what's inside. The derivative of the constant 2 is 0, and the derivative of sine is cosine. And that is the derivative of this example. Other things that we need to be comfortable with are the log properties, and these log properties hold for both the natural log and the common log of any base. So it's saying that if you have a product inside of a logarithmic function, you can separate the product by adding the log of each individual piece of the product. Similarly with division, the top minus the bottom. And if you have something raised to a power, the whole thing needs to be raised to a power, by the way, not just one term inside. And you could actually multiply that in front. These three log properties can make certain complicated problems much simpler to maneuver. For example, we are just going to simplify this using our logarithmic properties. So we can expand and we can condense. Right now, everything is condensed. Let's expand. So this is really a review of trigonometry in probably a pre-calculus course that you took where you learned log properties. But in many cases, especially when we start talking about implicit differentiation, these log properties can be really helpful. So if I'm using my log properties to solve this equation or to expand this equation, the first thing I'm going to do is I'm going to take this exponent and I'm going to bring it down as a multiplication in front. So I have 8 times this whole loggy thing, ln of x cubed plus x 4x squared minus 3x plus 2. Okay, now we do not have any rules that say that if we have an addition or subtraction inside of the log, there's nothing we can do. We can't separate that out. So we've done this part. Now, what did that do for us? Well, this means that now when we go to take the derivative, we can focus on the 8 just staying in front as a coefficient, and we look at a chain rule. Okay, so this is not x, so this would be a chain rule to take this derivative, and the outside function being the natural log. Now, I could have taken the derivative either way by bringing the 8 down or leaving it where it was, but that would be a chain rule inside of a chain rule. So by using a simple log property, we eliminated one of the chain rules from the original problem. So now to find the derivative of y, I have the ln function, which is 1 over the inside. So 1 over the inside function. Well, technically this is 8 times because this 8 just stays in front. So 1 over the inside function, x cubed plus 4x squared minus 3x plus 2. And we would then take the derivative of the inside function following our chain rule. So we have 3x squared plus 8x minus 3. I would probably, instead of 8 times the 1 over, I would just put that 8 in the numerator. It looks a little prettier that way. And again, you can take this inside function, which is being multiplied, and also write that 8 times those parentheses to make it a little more condensed looking derivative. Let's try another one. So here, this one is massively complicated. And if we tried to take the derivative of it as it is right now, we would have an outside function with a very complicated inside function. So that's a chain rule. Inside here, we have a quotient rule and a product rule and 3 other chain rules. Now, I don't know about you, but that sounds scary and very hard to organize and make sure that we don't miss anything. So let's use some of our log properties to dissect this problem and then see if we can find much easier derivatives to take. So what I'm seeing is inside this log, we have a product and we have a division. So remember, if there are things being multiplied inside of a log, we split those up to individual log calculations with an addition between, and the division would be a subtraction. So first, let's rewrite the products and the quotients. So I'm just rewriting y equals, we have ln of x squared plus 1 to the 4th power plus, because of this product, there's a plus, ln of x cubed minus 8 to the 5th power. Now we have a division, which is going to be a subtraction, minus ln of x to the 4th minus 8x squared plus 2 raised to the 6th power. Now I have 3 separate terms, meaning I can take the derivative of each term separately. That's already made my life a ton easier. But as we saw in the last example, I have a chain rule because there's an outside function natural log with something other than just plain old x inside. But that's also raised to a power, so there's a chain rule instead of a chain rule. So remember, I can bring all of these exponents down in front, and I would be saving myself a chain rule when taking the derivative. So I'm going to bring that in front, bring that in front, and bring that in front. Now I can take the derivative of each of the 3 terms separately, and there's only one chain rule per term. So let's do it. So the first one, I have 4 over, because it's 4 times 1 over, so we're just going to put 4 over, keeping the inside function the same, and then multiplying times the derivative of what's inside. Okay, so I'll simplify that after. Plus the derivative of the next term. So we have 5 over the inside function times the derivative of the inside, which is 3x squared and negative 8, just like positive 1 went to 0, minus 6 over x to the 4th minus 8x squared plus 2 times the derivative of that inside function, which is 4x cubed minus 16x and then plus 0, which we don't need to write. Okay, couple simplifications because we have very simple, it's not the second derivative, sorry about that. First derivative. We have some simple multiplications here. So this is 8x over x squared plus 1 plus we have 15x squared over x cubed minus 8 and minus, this one we'll just keep as is with the 6 times because I don't feel like distributing it through. It's not necessary. The other ones were different because they were just regular constants or coefficients being multiplied, so it made sense to multiply them. Ooh, that was an ugly line. And we just write this bottom function, x to the 4th minus 8x squared plus 2. Okay, and that would be the derivative made much easier by applying log properties. That concludes our presentation of inverse trig and logarithmic functions.